Okay, so today we're diving deep into a real cosmic puzzle. We're talking about PSR B0833-45, but you probably know it as the Vela Pulsar. This thing, it's like a celestial rebel, constantly breaking the rules of physics, and we're going to try and figure out why.
This isn't some super distant, obscure object. It's practically in our backyard, only 815 light-years away. But here's the really cool part. The Vela Pulsar is so important, it's literally on a map we sent to aliens. Yep, it's one of the 14 pulsars on the golden plaques of the Pioneer and Voyager probes. It's supposed to be a cosmic signpost pointing back to us, a true landmark for all of humanity.
So here's the deal with pulsars. They're what's left after a giant star dies. These super dense cores spinning with insane precision. They're basically nature's most perfect clocks, right? Well, not this one. The Vela Pulsar is, well, it's weird. It's a clock that can't keep time, a star that's not where it's supposed to be. It's a beacon that's just full of secrets.
All right, so here's our game plan. We're going to break down the case file on Vela. We'll look at why it's in the wrong spot, why its timing is so messed up, its weird light show, and why it's so cold. Then we'll tie it all together. First up, the mystery of the star that's out of place.
Okay, Section 1. Let's start with a really basic question. Where did this thing even come from? And, maybe more importantly, why is it just sitting there?
The theory is pretty straightforward, you know. A giant star goes kaboom, a supernova. It leaves behind this huge, expanding cloud of gas. Right in the middle of that chaos, the star's core squishes down into a super dense pulsar. And the explosion gives it a massive kick, sending it flying out from the center at incredible speeds.
So here's the kicker. This pulsar is about 12,000 years old. In that time, it should have moved a long, long way from the center of that explosion. It should be way out in the suburbs of its own remnant by now. But when astronomers actually looked, it's not. It's basically still hanging out at ground zero. It has barely moved at all.
And we're not talking about a small miscalculation here. The math said it should be moving at a certain speed, about 0.33 arcseconds a year. What we actually see? Less than 0.06. That's a huge difference. It's moving at least 6 times slower than our best models predict. It's like finding a cannonball right next to the cannon, moments after it was fired.
This was so weird, so baffling, that back in 1988, a couple of astronomers threw out a wild idea. They said, hey, what if the pulsar and the gas cloud aren't related at all? What if it's just a total coincidence they're in the same part of the sky? I mean, think about that. It completely undermines one of the classic examples of a pulsar and its birthplace. It was a huge deal.
Okay, so its position in space is a total head-scratcher. But let's move on, because if where it is a mystery, how it spins is a full-blown crisis.
Pulsars are supposed to be these perfect timekeepers, slowly, predictably spinning down. But every now and then, Vela just glitches. It suddenly and violently speeds up. The main theory for this has been that there's this weird frictionless liquid, a superfluid, sloshing around inside the star's crust. And sometimes, this superfluid suddenly grabs onto the solid crust and gives it a spin, transferring all its momentum in a flash.
So for this to work, for the glitches to be as big as they are, scientists figured this superfluid layer had to carry about 1.6% of the star's total rotational energy, or its momentum of inertia. And for a while, everyone was like, okay, 1.6%, that makes sense, problem solved. The model seemed to hold up.
But then, physics got more complicated. A little problem called entrainment popped up. It turns out that a lot of that superfluid isn't really freewheeling. It's actually kind of stuck to the crust, dragged along for the ride. So the amount of extra spin it has to give away during a glitch, it's way, way less than we first thought. So once you factor this in, how much of that rotational energy does the crust need to have to explain the glitches? The number shoots up from 1.6% to a massive 7%. That's a huge leap, and it just goes to show how one tiny detail in the physics can blow the whole problem wide open.
And this, my friends, is what scientists call the glitch crisis. The crust just isn't big enough. There's no physical way for it to hold 7% of the star's inertia. The math just falls apart. The standard model is broken, and Vela is the pulsar that broke it. It means our ideas about matter under these insane pressures, we're talking 1 trillion times denser than steel, are just plain wrong. Something else has to be causing these glitches. Maybe something happening deep down in the core.
All right, we've talked about motion and timing. Now let's talk about light. You know, we think of pulsars as these cosmic lighthouses, sweeping a nice, clean beam across the universe. But Vela? Yeah, its beam is anything but simple. Just take a look at this. If you look at Vela with a radio telescope, you see one single simple pulse. Easy enough. But then you look at it with visible light and suddenly it has multiple peaks. And in high-energy gamma rays, it's got two main peaks with this weird bridge of light connecting them. It's like the star has multiple personalities, and which one you see just depends on what kind of glasses you're wearing. And it gets even crazier. If you zoom in on just the gamma rays, the shape of the pulse actually changes as you look at higher and higher energies. The peaks change in brightness relative to each other, they get skinnier, and they even start to shift closer together. The complexity is just mind-boggling. So the big question is, why? Why isn't it just a simple lighthouse beam? What's going on in its powerful magnetic field that could create such a complicated light show that changes with energy? Whatever the answer is, it's going to tell us something fundamental about how these incredible cosmic particle accelerators actually work.
Okay, on to our last big puzzle. And for this one, we have to go deep inside the star itself. The problem? This star is way too cold. So, neutron stars start out unbelievably hot and then cool off over time. We have models that are pretty good at predicting how fast that should happen. But with Vela, it's just not following the rules. When we measure its temperature, it's only about 2/3 as hot as it's supposed to be for a star its age. It's losing heat way too fast.
There's really only one way for a neutron star to cool down that fast. It has to be blasting out an insane number of neutrinos from its core. And Vela's cooling rate is one of the fastest we've ever seen. This is a huge clue that something really exotic, something not in our standard physics books, is happening deep inside that core. It's like it's opened up a neutrino fire hose, just flooding the universe with heat and cooling itself down in the process.
So where does that leave us? We've got a star in the wrong place, a clock that can't keep time, a bizarre light show, and a core that's way too cold. You might think this is a failure, but it's not. It's an incredible opportunity. Vela is basically a perfect laboratory for pushing physics to its absolute limits.
So let's just run through the rap sheet one more time. 1. Its location is so strange it makes us question where it even came from. 2. Its glitches are so big they've broken our best models of super-dense matter. 3. Its light is so complex it forces us to rethink how these things even shine. And 4. Its temperature is so low it hints at brand new physics hiding in its core.
Every one of these puzzles is a clue, a breadcrumb, leading us to a deeper understanding of the universe. Vela is forcing us to question everything we thought we knew about nuclear physics, about gravity, about matter itself. So the real question isn't just about solving these specific riddles. It's about what else is hiding inside this incredible cosmic engine, just waiting to completely rewrite our textbooks.